Now we'll take everything that we've learned and put it together to solve a system of equations. We're going to do this using the matrix equation that we're going to convert from the system of linear equations. So if you recall the previous matrix algebra where AX equaled B, and we converted that to the matrix equation X equals the inverse of A times B, we're going to use this method by setting up the linear equation into matrix equations first, and then solving the matrix equation to solve the system of equations. So look at sample problem number 2. It says use a matrix equation and a graphing calculator to solve the linear system. Now I know you know a simple graphing calculator method to just solve the system of equations, and that would kind of defeat the purpose here, but that is a great way to check your answer if you're unsure of your final solution. So go ahead and try sample problem 2 by changing it to a matrix equation first and then solving the matrix equation for the solution. We'll start by setting up the matrix equation. Now we'll rewrite this matrix equation as the X equals the inverse of A times B. Now keep in mind the X and the Y stacked together represents our variable matrix. And we'll raise that to the -1 power to show the inverse. Remember, the order of these matrices is extremely important because of matrix multiplication. Your row and column agreement has to work. Then if we punch this into our calculator, you'll get the variable matrix equals to this resulting matrix. Now, here's the final part of this problem. We've solved the matrix equation and gotten a value for each of the variables. According to these matrices, equivalent matrices, the X equals to -7 and then the Y equals to -4. So the X equals to -7, the Y equals to -4. However, since we're solving a system of equations, we know that this X and Y represents a point, and that point represents the solution to our system of equations. Okay, so that's a good example using matrix equations. Now, we have one more down here. It's a little bit more complex, and it's probably something you've never seen before. But we have an equation, a system of linear equations with an x, y, and a z value. Now, this is a little different. You've probably never worked anything with 3 variables in it. Notice here that since we have 3 variables, in order to make this work, we actually need 3 equations. Now let me give you a good simple visual example of where 3 variables would be used. If you look at this picture here, we have an x and a y axis, but we also have included a z axis, and this gives us the opportunity to create 3-dimensional figures and then plot those points. So you can see the blue points here represent a point in space, in a 3-dimensional space, as opposed to a 2-dimensional plane that we normally have with the xy coordinates. So this is where the x, y, and z are going to come into play. You may use these a little bit more in physics later on, whenever you get into vectors and things of that nature. But this gives you a visual of how this particular problem is going to work. Now, that being said, we're not going to do anything different here. We're going to take the coefficients and make a matrix out of them, and then we're going to make a variable matrix, and we're going to solve it the exact same way. So take a minute or two to see if you can figure that out. Okay, so now I'm just going to go ahead and write out the solution and check it at the end to see how you did with the matrix equation. And we ended up with 3 values for the x, y, and z, and of course we would want to write these as a triple to represent that point in space. Okay, so there's a little practical application to matrix equations.